Okay, well, welcome to the second lecture in the series about the heart. And so this is, in a normal year, this would correspond to lecture 14, and the posting date of this will be on November 4th, 2020. So what are we going to do today? So we're going to talk a little bit about extrinsic innervation. And so here we're talking about how that intrinsic conduction system is modified by external factors. We touched on that briefly last time, but we're going to go into more depth. We're going to talk about ECGs, or what you might know as EKGs. We're going to focus on the cardiac cycle and define what we mean by cardiac output, heart rate, and stroke volume. We're still on chapter 18, and here's some extra videos that might help you learn some of the content. So I just want to start by doing a little bit of review from last class. And so specifically, this is a section I call Know the Flow. And so we're talking about the flow of the blood through the heart. And so we know that the blood is going to be returned to the right atria, marked here with RA, from the superior and the inferior vena cava. Pressure is going to build on the tricuspid valve. It's going to go into the right ventricle. When that ventricle contracts, it's going out to the pulmonary system. So there it's going to pick up oxygen. When it comes back, it's coming into the left atria, going down to the left ventricle. And then when this ventricle contracts, it's going out through the aorta to the rest of the body. Okay. We also talked about the intrinsic conduction system. So this is based on the idea that there's actually two types of cardiac cells. There's the contractile cells. So those are most of the kind of the meat in the myocardia here. And then there's the pacemaker cells. So most of these pacemaker cells are concentrated in the SA node here. The signal is then spread down to the AV node, down to the AV bundle. The bundle branches and eventually down to what are known as the Purkinje fibers. And so these are deep within the myocardium. And so this system, generally, we think of it as allowing the heart to contract as a single unit. You don't need external innervation in order for this system to work. And so if you took the heart out of the body, for example, it's still going to beat due to this intrinsic conduction system. I also noted last time that the signal pauses here for a really brief fraction of a second, so it's listed here as 0.1 seconds. And this allows the atria to contract really just a very small fraction of a second before the ventricles. Again, despite this, I mentioned it last time, we still consider the heart to contract as a single unit. As I mentioned, this intrinsic system can be modified by extrinsic or outside factors. These are concentrated in what we call the cardiac centers in the medulla oblongata. So this is the lower area of the brain. And this makes sense. We kind of think of this area as associated with more basic functions, things you don't really have to think about. And this should make sense to you because you don't really think about your heart beating each time it has to beat. You don't really consciously increase or decrease your heart rate either. And this is in contrast to the higher functions like creativity, which would be in this area here. So the cardiac centers, you have inhibitory centers such as the vagus nerve here, which is going to come down and it's going to inhibit the SA node, the AV node. You also have accelerator centers which do the opposite. Okay, so this is in the SA node and in the AV node, and then also areas of the myocardium as well. This vagal parasympathetic stimulation is actually something that's really important. And so this actually produces kind of a common dampening effect on the heart rate. And so normally the SA node, this intrinsic system, is going to set the heart rate at about 75 beats per minute. That's in the context of already being dampened by the vagus nerve. Okay, so if you were to remove the heart from its body, again, we're using that as an example, then you're no longer going to have this inhibitory effect on the SA node, and its kind of basal rate will go from about 75 to 100 beats per minute. So contrary to what kind of might intuitively make sense, if you take the heart out of the body, it might actually be beating faster. So I mentioned that there's two types of centers here. So the vagal, this inhibitory center here, is going through parasympathetic signals. This is hitting mostly the SA node and the AV node. Again, I showed this on the last slide, but the SA node and the AV node can also be positively influenced by the accelerator center. This will also stimulate more kind of directly the heart muscle as well, and also some of the coronary arteries as well. Okay, again, kind of the one that most people think of is this inhibitory function of the vagus nerve, and again, this is decreasing the basal heart rate from about 100 beats per minute. This would be what's happening if there's no external regulation, to about 75 beats per minute. Okay, so the SA node wants to go at 100. The vagus nerve is saying slow down. Let's keep it at 75. So there's a lot of electrical activity in the heart that should make sense, and it's obviously very important. And because it's important, we often want to measure it. And so I'm going to talk about how we might measure it and the types of things that it can tell us. So this is what we refer to as electrocardiography. And so the electrocardiograph actually refers to the machine itself, electrocardiogram, often abbreviated ECG or EKG. This is the actual kind of graph that it spits out. And I'm sure you guys have kind of seen these little outputs that these types of machines can give off. Okay, so this is telling you about the electrical activity of your heart. And again, I'm sure that you guys have seen these kind of patterns before, these kind of peaks and values in one of these kind of heart profiles here, these electrocardiograms. And we're going to go through what each of these things mean. But what I want to emphasize here is that electrocardiogram and what you see is kind of the peaks and valleys in one of these things. It's not, there's no simple explanation for why a peak might go up and why you might have a valley down in the other direction. An electrocardiogram is kind of the composite of all the electrical activity going on in the heart at a single time. It's not a tracing of a single action potential. Okay, and so the actual kind of math behind all this gets quite difficult, and so you really just kind of have to take my word for it of what each of these features means. Okay, just because it goes up, it doesn't necessarily mean it's a depolarization or a repolarization or vice versa. So we're just gonna kind of assume that what people have learned empirically by testing over time is correct. And so again, there's various kind of types of these electrocardiography that can be done. From the very, very simple one where you place a single lead kind of on your finger. The real ones, the ones that are done properly, is 12 leads and they're spread across the entire body. Okay, so it might look something like this. Sorry, I'm flipping back and forth here. So the leads can be placed all over the body, and again, it's going to measure kind of a composite of all the electrical activity that is going on across the body. Okay, as I mentioned, the math behind this actually gets quite complicated, and so trying to understand why this peak goes up, why this peak goes down, I think it's something that we can very safely say is beyond the scope of this course. Okay, so you don't need to know this slide. It's very simply to illustrate the concept that ECGs or EKGs, if you want to call them that, they can be very complicated. So we're just gonna assign kind of meaning to each of these features without worrying too much about how that's derived. So that being said, let's do this. Let's keep it simple. So these are measuring the activity of the things happening in the heart. And you can think of it as kind of mirroring what's happening with the flow of the blood. So that's why we reviewed that at the beginning of the lecture. And so the first feature of this is referred to as atrial depolarization. And for reasons that still aren't clear to me, this starts with P. Okay, so not A, it's just starting with P. Okay, and then each of the features is going to be labeled with the subsequent letters of the alphabet. So this little peak represents atrial depolarization. So that's going to happen right before the atria contract. Okay, and then that's what this P peak represents. Then you have something called the QRS complex. This represents mostly ventricular depolarization. Okay, so you have the atrial that's depolarizing, and then the ventricle that's depolarization. And so this, again, is called the QRS peak. And then you got a bit of time here. This is called the ST interval. And then after this, you see ventricular repolarization. So every time something depolarizes, it's going to then subsequently repolarization. So with that, you should be asking, well, what about the atrial depolarization? Where is that? I don't see that on the graph. And it's true, you don't see that. It's thought to actually be hidden within this larger QRS peak. And so in terms of these features here, this is representing atrial depolarization, ventricular depolarization, and also the repolarization of the atria is hidden within this QRS peak. And then the ventricle repolarization, because all the actions already happened, can be seen afterwards, and this is called the T wave here. Okay, and so these are the main features here, and this just represents what I've just said. So this is just simply a different way of representing what I showed on the previous slide. So this is something that's really important. In a minute, we're going to try to match this up with what we know is happening in terms of contraction of the heart and the flow of the blood. And so I really want you guys to understand this. So once your SA node fires, we know that the SA node is going to fire via the intrinsic conduction system. You begin to get the depolarization of the atria. And again, that's this P peak here. This is complete at this stage right before the QRS. Again, the QRS is going to represent both repolarization. This is the change from yellow or orange maybe to red, and the depolarization of the ventricle. So this is reflected in the change of the color here. Okay, so that's what we're seeing with the QRS peak, both of those features. So by the time we get to here, the ventricles have been completely depolarized. Okay, and so you're going to have an association of a contraction at that time. The T wave is the beginning of the repolarization, and that continues until after the T wave until you get a new P wave. Okay. So again, this is simply a different way of looking at the exact same information that is presented on the previous slide. Often, if you look at things using different sets of diagrams, then you'll have a better chance of understanding what's going on. And it is really important to understand what's going on. I don't think you'll have too much luck just trying to memorize these things. You really want to understand how everything connects together. So let's go through it one more time with the first diagram. Again, very important process we're looking at here. P wave. This is, I think I called it a P peak, that's fine as well. It's atrial depolarization. Next big feature is this QRS. QRS complex or peak, wave, whatever you want to call it. This represents both ventricular depolarization and atrial repolarization. So those were the two colors, for example, on the previous slide. The next really definable feature is the T wave, and this is ventricular repolarization. So again, these are the key features of what we call here. This is going to be an electrocardiogram. Okay. So the reason these things are important is not just to kind of tell you got your treadmill plugged into your finger there. They can also tell us really kind of important things about how our heart is functioning as an important organ in our body. And so this is what the normal electrocardiogram looks like. So you can really identify the P peaks, you can identify the QRS and then the T wave in each situation. Okay. Now, normally we know that the SA node is going to be setting the beat at 100 beats per minute. And we talked previously that it actually wants to go higher, but it's the vagal nerve kind of telling it to slow down a little bit. But one thing that can go wrong is that your SA node doesn't function properly. Okay, and this is what's called a junctional rhythm, and here kind of the defining feature is the absence of that P wave altogether. And you're still okay in this situation. The AV node can actually take over and it can pace the heart on its own, but it's not as good. And so really there you're only looking at about 40 to 60 beats per minute. And so this can actually be fixed with an artificial pacemaker implanted into the heart. There's something else called second degree heat block. That's kind of the companion piece to the junctional rhythm. So if junctional rhythm is all about the SA node, then second degree heart block is all about the AV node. And this is when the AV node fails to conduct the impulses that are coming down the line from the SA node. Okay, so as we said previously, the AV node is supposed to collect those impulses. It pauses for a short period of time and then sends it down through the rest of the heart in the myocardium. So when you see a second degree heat block, really kind of the defining feature is that usually there's multiple P waves for every Q or S peak. Okay, so this is the SA node that is kind of sending the electrical signal down the line. The AV node doesn't do anything about it, and so the SA node keeps sending that signal. Okay, and that's what's called a second degree heart block. Then there's ventricular fibrillation. This is characterized by really kind of disorganized electric activity within the heart. You can't really identify any specific P waves, T waves, QRS peaks. It's really kind of just a mess. And so if you have a profile, an electrocardiogram that looks something like this, it's a sign that you're in big trouble. It's a sign of an acute heart attack, so a heart attack which has just happened, or even after an electrical shock. Okay. So those are all pretty major issues. So if you went into the hospital and you had one of these things, it'd be pretty easy for somebody to diagnose those. But this is really kind of a field unto itself, and I hinted at that with kind of the math behind it. There are people that spend their entire career trying to figure out what these things mean, and it's lucky for us that they did. But there's more subtle things that can be pulled out with these profiles. And so, for example, an enlarged R wave could indicate enlarged ventricles. You can have a depressed or elevated T segment here, and the depressed or elevated T segment, that will indicate a cardiac ischemia. And so ischemia is a word that basically means a lack of oxygen getting to the myocardium. Okay. You can also have a prolonged Q to T interval, so from here to here, and this reveals a repolarization abnormality, and this can increase the risk of ventricular arrhythmia. Okay, and so this is basically a minor issue which can lead to something which is much more dramatic. Okay, now let's get into some of the mechanics of heart function. So first of all, I want to come and make a few definitions. So systole, this is a period of heart contraction. Then there's diastole. This is a period of heart relaxation. And together, these two things make up what we call the cardiac cycle. And so the cardiac cycle is just the flow of the blood through one complete heart beat. And so this consists of systole and diastole in each case. Okay. Ultimately, our goal when we think about the cardiac cycle is to understand this very seemingly complicated figure, okay? And so the cardiac cycle involves looking at electrical activity in the heart, it involves looking at the pressures in the heart, and also the flow of blood. And we've talked about some of these things already. So we've talked about the blood flow, okay? So again, I'll go over it again. It's flowing from the right atria into the right ventricle, it's going out to the pulmonary system, and then it's going to come back into the left atria, into the left ventricle, and then going out to the systemic system. Okay, and that's shown in these diagrams here. And we just talked about this. We talked about the ECG profile. So there's the P wave, there's the QRS complex, and then there's the T wave. And the point here is that you can see that these features match up. And so you can see that the P wave is associated with the final stages of atria contracting and blood filling up the ventricle. Okay. Likewise, the QRS peak is always going to occur right before you have a full ventricle contraction and ejection of blood out of the ventricle. Okay, so what we're doing with this diagram is trying to match up the electrical activity with the blood flow. Okay, one more thing that I'll point out is the volume. The volume should actually make quite a lot of sense, and so this is actually looking at the volume here just in the ventricles. It's only kind of one ventricle, but again, both sides of the heart are functioning in the same way. So what's true for one side will also be true for the other. And so the blood amount in the ventricle is going to increase over time, and that's because it's flowing really directly from the right atria into the right ventricle, and then it's going to very abruptly decrease as you contract. and that's because the contraction is forcing that blood outside of the ventricle. So we've really hit already three of these things. The blood flow, we've gone over that extensively. The electrocardiogram, we know that each of these electrical activities is followed by a contraction, and that should make sense to you. It's the electrical activity which is stimulating the contraction. And then we looked at the volume. So volume increasing slowly in the ventricle as blood comes back and fills the ventricle from the atria, and then a very quick contraction, and that blood is ejected from the ventricle, and it goes through either the pulmonary or the systemic circuit, depending on which side of the heart that we are thinking about. Now, there's a little bit more we want to talk about in terms of pressure, and we'll come back to that at the end of the lecture. So now we want to talk a little bit about the idea of regulation. And so obviously it's very important that your heart is regulated in terms of its cardiac output. And so what do we mean by cardiac output? Cardiac output is the amount of blood which is pumped out by a single ventricle in 1 minute. Okay, so that's just how it's defined. And this is equal to the heart rate times the stroke volume. Heart rate we already know, so intuitively you know what a heart rate is. What is a stroke volume? Stroke volume is the amount that is squeezed out with each contraction out of that single ventricle. Okay, so the cardiac output is going to be kind of in a mils per minute. So how many milliliters or liters of blood are you putting out every minute? And this is determined by the heart rate. This is in beats per minute. As we said, the average we can think of as about 75 beats per minute. Again, the SA node wants to go faster, but it's the vagal inhibitory stimulation that's telling it to slow down. And then the stroke volume is how much is coming out with each contraction of the ventricle. And so to get cardiac output, we simply multiply across heart rate times stroke volume. So 75 times 70 equals 5,250. And if you don't believe me, you can do it yourself. And that's in mils per minute. We can convert that to liters simply by dividing this value by 1,000. So this means that your heart is really outputting over 5 liters of blood every minute. So that's actually quite a bit. But this is actually the resting rate. Okay, so when you're exercising, it can get even higher, 20 to 25 liters per minute. If you're a trained athlete, most of us are probably not, but if you're a trained athlete, it can go even higher to 35 liters per minute. Okay, so the heart is really kind of a well-oiled machine, and it can function at a very high level if necessary. There's something that we refer to as cardiac reserve. Cardiac reserve is simply the difference between that basal or resting heart rate, so 5.25 in this case, versus the maximal. So I said heart rate, I meant cardiac output. The basal cardiac output versus the maximal cardio output. So it'd be the difference between, say, 20 and 4. So the cardiac reserve in that case would be 16 liters per minute. Okay, so this is just the sample calculation for cardiac output. So now we want to talk about the two kind of features, so stroke volume and heart rate. And we'll talk about them both individually. So again, these are the two factors that are making up cardiac output. So we're going to start by talking about stroke volume. Again, stroke volume is the amount that's pushed out with each contraction. And it's defined in terms of just one ventricle. And so mathematically, we talk about stroke volume equaling the end diastolic volume minus the end systolic volume. And probably a unnecessarily complicated way of saying that stroke volume is equal to the amount of blood that's loaded into the ventricle versus that which remains once the ventricle contracts. Okay, so end diastolic volume is just that. It's the amount of blood that's flowing into the ventricle when they're relaxed. So that blood's coming, ultimately being returned by the vena cava. It's flowing through the right atria, for example, into the right ventricle. Same thing is happening on the other side of the heart. And when that ventricle is completely as full as it can be before a contraction occurs, that's called the end diastolic volume. The end systolic volume is the amount that is left over after the contraction. And implicit in this is the understanding that when the ventricle contracts, not every last little drop of blood is actually going to make it out of the ventricle. There's going to be some that actually remains behind. Okay, and so we'll look at that regulation in a second. And so the normal kind of stroke volume that you have, the amount that's output, is actually about 70 beats, 70 mils per beat. Okay, so the ventricle in each case is going to be outputting 70 mils of blood per contraction. And the way we get to that number is that there's about 120 mils that are loaded in there, and there is about 50 that remain. So again, end systolic volume is just that amount that doesn't get out of there after contraction. If you're having trouble thinking about that, you can think of it like a water bottle. Okay, usually I use my example, my coffee cup that I bring with me to pretty much every single lecture. So this is the amount of say water in the bottle. It's 120 mils after you fill it up with the tap. Okay, and then the end systolic volume is the amount left over after you squeeze that bottle as hard as you can. Now, despite the fact that you're squeezing the bottle as hard as you can, not all of that liquid is going to pop out. Some of it's going to remain. And if you don't believe me, you can grab a bottle. You could try it for yourself. Okay, so this is how we define stroke volume. And again, that's paired with heart rate to determine your cardiac output. So again, I just want to talk about these volumes. I touched on it a little earlier, I guess. I think I meant to talk about it now. But the end diastolic volume in this case is going to be the volume right before the ventricle contracts. Okay, and then the end systolic volume, which is this line here, it is after contraction. Okay, so again, this looks like a very complicated diagram, but it's really not. We've gone over this now for 2 lectures. We talked about the electrical events. We just went over this in a little bit more detail, and I'm going to come back and talk about this again at the end of the lecture. Okay, so this just talks about some of the pressures associated with this, and I think you'll find that it actually makes a lot of sense. Okay, so there's 3 things that affect the stroke volume, or the amount that the ventricle can eject each time. And these things are called preload, contractility, and afterload. And so we'll look at these one at a time. Again, looking at stroke volume, part of the equation that's determining cardiac output. Okay, so stroke volume is regulated by preload. This is the first thing we want to talk about. This really refers to kind of the degree of stretch associated with the heart muscle. Okay, and basically the idea here is that the heart is never at rest. The cardiac muscle within the myocardium, particularly within the ventricle, is not at its optimal length for contraction. As you load blood into the ventricle, what happens is that the fibers stretch and they reach a point at which they're able to give the maximum contraction. Okay, and so this is actually a very important concept, and it's called preload. Okay, so it's the degree of the stretch of the heart muscle. Again, to go over that again, the point is that as you load more blood into the ventricle, you're going to have the heart muscle is going to stretch. At a certain point, you're going to reach the optimal length of those fibers to give the strongest contraction. And once that happens, then you can get a very strong contraction. Okay, and so this is also something that's referred to as Frank Starling's law of the heart. And so the Frank Starling law of the heart basically says that within defined limits, the heart is going to pump whatever blood it receives. Okay, so as you stretch those fibers more and more by loading more blood into the ventricle, the heart is able to pump it, and it's able to pump it because you're stretching those fibers to what is ultimately the optimal length for contraction. Okay, and so you can see that there's a pretty linear relationship between the diastolic volume, that again, that's going to be the amount of blood that's loaded into the ventricles when they are relaxed, versus the systolic force. So systolic force is referring to the force of contraction during that phase of the cardiac cycle. Of course, like most kind of relationships in biology and physiology at very dramatic levels, that relationship is going to break down a little bit. So that's the first thing that regulates stroke volume by preload. Preload is defined as the stretch of the muscle fibers. Okay, and within defined logical constraints, the Frank-Starling law of the heart dictates that whatever that ventricle gets, ultimately it is going to try to pump it. Okay. So what regulates preload? What regulates the amount of cardiac stretching? Well, it should be obvious that the most important thing is the amount of blood going into that ventricle. Okay, that's going to determine how much stretch there is. And so this is determined by the venous return. So how much blood is coming back from the superior and inferior vena cava, for example. That's going to determine how much stretch you get ultimately of the ventricle and ultimately how hard of a contraction that you're going to get. And so this venous return itself can be regulated as well. And so if you exercise more, for example, you're going to get increased return and your cardiac output can go up. Okay. And if you look back at the equation, that should make some sense. Okay. The second thing that regulates stroke volume is contractility. And so this is basically any other regulation of the ability to undergo a contraction that's independently of muscle stretch. Okay, so any increase or decrease of force that's independent of that Frank-Starling law of the heart, this is referred to as contractility. And this can be regulated by a number of different factors. So it can be regulated, for example, by the amount of calcium. So we know that calcium is really important for muscle contraction. If there's more calcium around, then regardless of whether your myocardium is stretched to the appropriate levels or not, you're going to have a better contraction. Okay. Just as there's positive things that can increase contractility, such as high calcium or epinephrine, there's also things that can decrease it. So one example is going to be increased extracellular potassium or chemicals that prevent calcium from being uptake into the cell. Okay. And so why is calcium so important? Calcium is important because it can regulate contractility through what we call a second messenger system. And I'm hoping that Dr. G went over some of this for you, but I really like this stuff, so I'm just going to go over it briefly myself. And so chemicals such as epinephrine, and so epinephrine we noted here, here it is what's called a positive inotropic agent, and this increases contractility. Again, this is independently of anything we associated with the Frank-Starling law of the heart. Okay, this is additional impacts on contractility. So we also see that calcium can increase contractility, or epinephrine works in part by allowing the cell to have access to more calcium. So epinephrine or norepinephrine, which for the purposes of this slide, we're going to consider to be the same thing. This can interact with receptors, and so receptors are membrane proteins which are bound on the outside of the cell. And this can activate proteins which are called GTPases. GTPases will basically hydrolyze GTP, and when they hydrolyze GTP, a new molecule of GTP can come and bind, and then this G protein bound to GTP, this will then travel along the membrane here and interact with another protein called adenylate cyclase. This is also a membrane-bound protein, and its job is to convert ATP to something called cyclic AMP. So let's just review that already. So norepinephrine is activating a G protein. G proteins in its GTP-bound state will activate something called adenylate cyclase. This will convert ATP, so ATP you should recognize as the energy currency of the cell, to something called cyclic AMP. Cyclic AMP, it does a lot of things. One of the things that it does in the cell is it can activate something called a protein kinase. A protein kinase is an enzyme that takes phosphates also from ATP actually, and puts it onto to other proteins. And when you put phosphates onto proteins, it can change what they do. Okay, so CAMP will activate this kinase. The kinase can then add phosphates in a reaction we call phosphorylation to different types of proteins. Many of these are membrane channels that regulate the amount of calcium available. So this can include release of calcium from the sarcoplasmic reticulum. This is a fancy version of the endoplasmic reticulum, or membrane proteins that are within the outer membrane of the cell, and this allows more calcium to come in. And you should remember from Dr. G's lectures that calcium is going to increase your contractile strength. Okay, so this is an example of regulation of stroke volume by contractility, and just going a little bit in depth into some of the mechanism here. Okay, so norepinephrine is ultimately working through calcium as well. Okay, the final thing that can regulate stroke volume is something called afterload. Afterload is simply, the easiest way to think about it is the back pressure put on the blood that's trying to be pumped out. So imagine there's, this ventricle contracts here and there's blood wants to go out in this direction. So follow my cursor, going out in this direction. But there could already be fluid there. And that fluid is going to basically put pressure backwards. Okay, so it's the equivalent of throwing a baseball in air where there's no back pressure and throwing a baseball in water where there is back pressure. Okay, and so that's what we call afterload. That's kind of the pressure that is exerted by the blood back into the ventricles. And you can have this both in the pulmonary circuit, and then you can also have back pressure going in this direction to prevent blood from coming out of this ventricle. So that's part of the reason why you don't eject all of the blood that is in the ventricle. So if we go back to our example of the water bottle, for example, that's like trying to squeeze out as much water as possible when somebody else is putting pressure on the top of that bottle. Obviously, you're not going to have quite as much fluid coming out of the bottle in that circumstance. So those are the three things that are regulating stroke volume. The other thing is heart rate. Heart rate is, again, a little bit more intuitive to understand, so it's the number of beats per minute. And this can be also impacted by a variety of different things. So the autonomic nervous system, so we learned about this already at the beginning of the lecture, various chemicals, and then other factors, which of course are going to work probably through one or two here. So again, let's look at these one at a time. So the heart rate is regulated by the autonomic nervous system, or the ANS. So again, that basically that sympathetic nervous system that can be activated by emotional or physical stressors. There's epinephrine or norepinephrine. This can bind to the beta adrenergic receptors. And again, this is going to regulate contractility, but it can also regulate the rate at which the pacemaker is firing as well. Okay, so there's multiple effects of some of these chemicals, such as epinephrine or norepinephrine. This second messenger system that I went into detail, so the GTP binding to the adenylate cyclase, kinase activation, this can influence both heart rate and stroke volume. Okay. One of the most important things when we talk about heart rate regulation, again, is this vagal tone. Okay, so vagal tone is this kind of inhibitory effect that's working on heart rate. Okay, and so again, normally your SA node wants to be going at about 100 beats per minute. The vagus nerve basically pushes that backwards to about 75 beats per minute. So it's a decrease of about 25 beats per minute. So if you were to cut the vagus nerve, then you're getting a heart rate of about 100. Okay. One concept that I want you guys to be thinking about is this something called the atrial reflex, or also referred to as the Bainbridge reflex. And basically this means that it's basically a reflex that exists when you have increased venous return, so increased blood coming back through the superior and inferior vena cava into the atria. As those atrial walls are filled, so as they begin to fill with blood coming back from the rest of the body, for example, you're going to be stimulating that SA node to fire faster. Okay, so the idea being that, hey, there's more blood coming back, let's get it out of here as soon as possible. Okay, so this is what's called the atrial or Bainbridge reflex. There's a whole host of chemicals that impact heart rate. So hormones, again, here's epinephrine. We've already talked about this quite a bit, but there's a lot of different things. So calcium itself, we talked about how epinephrine actually works through calcium, and potassium can actually have the opposite effect. Obviously, these things are very important for heart function, and so imbalances are going to be very, very dangerous. Okay. Finally, heart rate can be regulated by other factors. And we won't go into too much detail here, but heart rate can be regulated by age, sex, and so females generally have faster heart rates than males. By exercise, you should be well aware that exercise increases your heart rate. Trained athletes can actually have a slow heart rate, and body temperature. And so this one might seem kind of counterintuitive. Trained athletes can have a slower heart rate, but the idea is that things are working that much more efficient. And so your body can get away with something like Usain Bolt, for example, has 33 beats per minute. And I always say that, well, let's just say that it's more than 33 beats per minute. When your heart is beating very fast, we call that tachycardia. So that's, greater than 100 beats per minute. Obviously, a resting heart rate of even like 85 or 90, that'd be considered tachycardia to some degree. And then brachycardia, this is going to be less than 60 beats per minute. Under most circumstances, that's possibly a bad thing. In athletes, it may actually be a result of long-term endurance training. Okay. So when we look at this all together now, again, kind of the point here is that cardiac output is going to be impacted by stroke volume and heart rate, and there's a whole host of things that impact each of these things. Okay, so if either stroke volume or heart rate go up, then that cardiac output is also going to go up. And so one thing that I mentioned at the beginning of the course is that one thing that the book is really good for is kind of providing these types of diagrams and going over them in a little bit of detail, so that if you come across kind of a question that allows you or forces you, I suppose, to integrate some of this information in an exam, you'll have already thought about it and you won't have to do it on the spot. So I encourage you to check out this diagram and see if you can use your logic and figure out how all of these different connections make sense. If you have questions, of course, that's what those Mondays at 2:30 p.m. are for. Let's just go back to this at the end here. And I just want to go through things again, but add on this little bit of pressure. And so blood flow, this is all kind of the different parts of the cardiac cycle. We're looking at what's happening with the blood flow, looking at what's happening with the electricity in the heart, volumes, and then eventually pressure. So blood flow, again, blood is coming back from we'll look at just the right side. It's coming back from the superior inferior vena cava, going into the atria. It is going to empty into the ventricle, and then eventually the ventricle is going to contract, and that blood is going to go out of the heart towards the pulmonary circuit. Same thing happening on the other side, except for the blood is going out to the systemic circuit, which just means the rest of the body. Okay, so when we talk about the cardiac cycle, these are given various names. So the ventricular filling phase, oddly enough, is when the ventricles are beginning to be filled. Isovolumetric contraction, this is this brief moment in time where basically there's not too much going on. The ventricles are filled. It's right before contraction occurs and these valves are closed. So despite the fact that it's called isovolumetric contraction phase, there's actually no active contraction going on. Okay, it's the very split second before anything major is happening. When those ventricles contract, that's where we're getting the ventricular ejection phase, and that's the blood going out to the rest of the body, or in the case of the pulmonary circuit, out to the lungs. Isovolumetric relaxation phase is basically the system restarting again as the blood is making its journey either to the lungs, again in the case of the pulmonary circuit, or to the rest of the body in terms of the systemic circuit. So the electricity on top, we know that the P wave comes first. This represents atrial depolarization. We have the QRS complex. This represents ventricular depolarization. And then the T wave is representing ventricular repolarization. Where's the repolarization of the atria? This is hidden within this QRS peak or QRS complex as well. The thing that you want to realize is that these major depolarization events are happening right before the contractions. Okay, so you depolarize, the energy has spread through the entire heart, and then it can contract as a unit. So if we look at what's happening with the ventricle, for example, you have this QRS complex and the ventricular depolarization that's happening, and then the very next phase is the ventricular ejections phase. So the electricity has to spread throughout the heart, and then it's set and ready to contract, which is the next phase. Okay. We also talked about the volumes. So in this case, we're looking at the volumes going into the ventricle, and this is steadily going to increase. And so in this phase, what's happening, the ventricular filling phase, is that the blood is coming back from elsewhere in the body. So if we're talking about the systemic circuit, it's going to come back and end up in the right atria, and this is going to empty into the right ventricle. Okay, so this is the ventricular filling phase, and so the volume of blood that's accumulating within that ventricle is going to slowly increase over time. Okay, and so basically the next big change is a loss in that volume, so that's what's happening with the ventricular ejection phase. And again, right before you get that ejection is when you have that spread of current throughout the entire heart. Okay, so then we've gone over each of those parts. Let's just look at the pressure of what's happening. Okay, so there's a variety of different diagrams here. Let's basically look at them in turn. So first we're going to look at the atrial pressure. And so the pressure in the atria, and so that's this chamber here, is usually kept pretty low. And the reason it's kept low is that you don't need to accumulate too much blood in the atria until that valve opens and things start to empty into the ventricle. So as you get fluid moving from the atria to the ventricle, there's not so much pressure that's happening in the atria. Okay, so the pressure is being relieved by the opening of the valve. You're going to get a little increase in pressure as the atria contract. As that atria contract, the job of it is really just to get that last little bit of blood into the ventricle. Okay, and then throughout the cycle, basically the system is then going to reset again. Okay, you have a little blip and weirdness in the atrial pressure here. This is caused by the contraction of the ventricle. Okay, so this is that's the atrial pressure. It's usually kept low. We see a little bit of a rise happening when the atria contract just before the last little bit of blood is moved into the ventricle. Okay. Next, we'll look at the ventricle. So the ventricle, again, the pressure is going to be very, very low, and that's because it's not full. Okay, so it's not full, and the valves are open. Where you get the very large increase in pressure is during the ventricular ejection phase, and this is because the heart is contracting, the space for the blood is smaller, pressure goes up, and that's why it's pushed out of the heart into either the pulmonary or the systemic circuit. Finally, we'll look at the pressure in the aorta. That's going to be going down, and it's going to continue to go down at the beginning of the cardiac cycle until the ventricle contracts, and it's going up during that circumstance because you're pushing more blood into the aorta. Okay, so as we get more blood, then the pressure within that vessel is going to increase. And we're going to talk about pressure in blood vessels within the next lecture. As the ventricle begins to relax, you're going to see that pressure come down. There's a little blip here. This little blip actually represents the backflow of blood that happens against the aortic valve. Okay, so this is a defining feature of that event. Okay, so again, going through everything, we have the blood flow, we have the electricity, we have the volume flow, and the different changes of pressure. Okay, and again, take a look at this. It's in the book. Try to figure it out on your own. And if you need more help with this, then this would make a great item for discussion during Monday's Q&A session. Okay. Cardiac output can lead, if there's defects, it can lead to congestive heart failure. Basically, all I want you to know here is this definition. And so the definition of congestive heart failure is that cardiac output is so low that the tissues are not getting their needs met. Okay, so you're not delivering oxygen to those tissues and you're not removing carbon dioxide. Okay, this is a progressive condition, and so if you start to have congestive heart failure and it's not treated, it's only going to get worse. Okay, so the last thing I wanted to mention here is that some of you might not know that the University of Ottawa actually has a research institute called the Heart Institute. And there's a whole host of amazing researchers here that maybe at some point within the next couple of years, you guys might actually get the opportunity to work with. And so U Ottawa has some really great research opportunity for undergraduate students. And so hopefully as kind of the COVID-19 situation improves, then students will be allowed back into research labs and you'll be able to work with some of these individuals. So the next bunch of slides, just like I showed last time, are just questions that are very similar to the type of thing that you guys might see in an exam. And so again, test your knowledge, and if you have any questions, we can go over this during Monday's live session. Okay, so that's it today. In the next lecture, I'm going to go over blood vessels and talk about how we get blood from the heart to the tissues in the body, and how when deoxygenated blood is output from those tissues, how it gets back to the heart. Okay, so we'll start to connect things together. As always, if you have questions, please let me know, and I will see you next class.